Good afternoon. Welcome to the Technical Libraries Have I Got a Story for You. This afternoon's story is the 21st in our ongoing series. As you can see, we do videotape them and they're all available for checkout. Our storyteller this afternoon has worked here at NOC Weapons Division for 33 years as a physical scientist. She has worked as a project manager, a technical project manager, a technical project officer for many different groups, both on the local level as well as internationally. She has published more than 200 technical papers. Most recently, she had an invited publication for the 8th International Symposium on Special Projects in Chemical Propulsion that was held just last November in Cape Town, South Africa. So great time getting to travel and do those wonderful things. Please join me in welcoming NAVAIR Fellow Alice Atwood.
Thank you very much. It is a pleasure and it's a very honor to be invited to speak to you today. A lot of the things I'm going to talk about, many of you in the audience know more about than I do. So if you're sleepy, it's a good time to catch a little nap, get some refreshments, and then you can catch up with us when you get to some place maybe that you haven't heard about. You mentioned Cape Town. Our branch head, Fred Bloomshield, was also an invited speaker at that meeting, as was Matt Gross, who is also a member of the group. So we had a very strong attendance from our team. So with that, we'll start. The question you might ask is, who in the heck is Alice? And what did she do at China Lake? Next. I'm a physical scientist. I work in the Combustion Sciences branch, and it's in the Energetics Research Division. I got a bachelor's degree from the University of Utah in 1974, and my husband and I moved to China Lake in 1976. Now I mention this because Ken is the person who was hired by China Lake. I just came along. We were newlyweds, and so he's to blame for my being here. I started working in April of 1977, and since we're telling a story, there was no visit. Ken accepted the position here at China Lake without ever coming down for a site visit. And we jumped in our 2 old cars in Utah, and we drove down here to move here. And it was in January, and we left 1.5 feet of snow in Salt Lake City. And when we came down and got to about St. George, it was like heaven. So I said to Ken, never let me complain about the heat. Have I complained about the heat? No. Good. Okay, so imagine I stop in Barstow for directions to get to 395, and the guy in the gas station said, "Lady, you're going into God's country. No one else wants it." Okay. So we drive some more. I get to Red Mountain, Johannesburg. It's like, Red Mountain, Johannesburg, what am I getting into? So when I got to Ridgecrest, things really looked good. Okay, and we've been here ever since. So could you hit that again, please? A long time ago, we were all supposed to be empowered and have personal mission goals. And I really clicked into it. And so this is mine. I'm going to share it with you. It's to provide the Navy a unique experimental capability relative to energetic material combustion. So that's my personal mission goal, and I hope I can inspire you to have yours. We joke that I'm old as dirt. This is dirt down here. It's actually a skeleton from the La Brea tar pits, and I've never been that thin, so I don't think I'm quite dirt yet. Okay, next. Can't do anything alone. You never test alone, you never work alone. And without this team, this presentation would certainly not have happened. And certainly, I am indebted to every one of the people listed here. Next. So, what do we use these for? They are used to gain understanding, looking at ignition and combustion, and we do a lot of them. And I hope today to weave together these tests to give you a story about ignition and combustion behavior. Next. From a very simplistic standpoint, what we want to know is something about the sample, the stimulus, and its response. Very simple. Next. So when we talk about sample, I'm going to be talking a lot about propellants today, but it also applies to explosives and pyrotechnics. We're going to focus on solids. propellant in itself often presents the largest target when you're thinking about something that's coming under, say, attack from an insensitive munitions concept. So that's something to think about. And we have two regulatory bodies that we have to be concerned with. One of them is hazards classification. That's for transportation and storage. That's the placards on the trucks you see driving around. And that's the 1, 1, 1, 2, 1, 3 kinds of things you hear talk about. And the other is for our IM, insensitive munitions. And so both of them are pretty critical. Okay, let's go to the next. When we talk about energetic materials, there's a lot of them. Explosives, propellants, pyrotechnics, and even the neat ingredients. I was very honored to be able to work with Dr. Arnie Nilsson in our chemistry division on CL20, and it's an amazing compound, and it was an amazing piece of work, a real honor to work with a fine gentleman. Next. So we talk about stimulus. Usually we break them into two parts. The mechanical stimulus, which is, you could say, shock or impact, and then a thermal stimulus. That can be either direct or indirect fire. And usually accidents, you're going to raise your hand and say, Alice, usually accidents involve both mechanical and thermal stimuli. And a couple of examples, bullet and fragment impact and transportation accidents. Usually you have an accident, there's an impact, and then there's an ensuing fire. Next. So when we talk about response, what do we mean? Lots of people think about detonation. Well, there's a lot more to it than that. You can have something from nothing clear up to a detonation. And we want to understand what is it that will cause our energetic to progress up to that high energy or more violent reaction. Next. So we're going to focus on combustion-driven events. Usually when we're talking about combustion, it's usually from the standpoint of, is my rocket going to fly? Or how far is my rocket going to fly? We want to know about ignition, flame spread, and then the steady state burning. And from a hazard standpoint, we need to expand our horizons a little bit. We need to expand our viewpoint. Next. So let's start with ignition. It's a process. From our definition, it is the process and the successful completion of that process. It's the beginning of every combustion event. Propellant must ignite reliably in the application, but immune to inadvertent. I mean, it's going to go when you want it to, but not go when you don't want it to go. If it doesn't ignite, your motor and payload become an impact hazard themselves. And you can have significant blast and overpressure without true detonation, and we're going to look at a film of that today. And the payload itself may present a hazard. So like if you have a nuclear battery on board, could cause you some problems. Inadvertent propellant ignition also creates a thermal hazard. Some people in our group have been studying this, and many people I think in this audience have worked on that, where if a rocket motor in a building caught on fire or in a storage building caught on fire. Next. Okay, here's the real deal. This you can find on the internet. It was a firing of a Black Brant rocket on 6 March 2005, Poker Flat, Alaska. Good thing it was in Alaska. Second stage did not ignite. The rocket findings were the igniter functioned but failed to ignite the propellant grain. I show this one because Mr. Ford had the opportunity to work with these people. The propellant is made in Canada, and they sent us propellant. We tested it for them. And we've worked with them on 2 other occasions in helping them design their improved igniters. Next. So what do we use for that? We have a CO2 laser that is provides radiant thermal stimulus. We have some lensing. We have a sample holder. And what we do is we vary the amount of time that we expose our sample to get an idea about how it's going to ignite. So next. We plot our data in log time versus log energy. I'm going to show you some of these plots. So we'll spend a little bit of time with this. And if we pick a flux level here, say, we start to heat our sample, If we turn our laser off in this region and look at our sample, we see nothing. It's not until what we call first light or first gasification that we start to see something going on the sample surface, some erosion, if you will, coming off the sample. But many times, the sample does not continue to burn. It's not until we reach what we call a go-no-go ignition locus that if we remove that energy, the sample will continue to burn. And from our perspective, that's the point that the thing is truly ignited, not down here. Now, my European colleagues would argue that that is. So we have some open debate here. Now, the relationship between these two lines is very much a function of the energy, the flux, the pressure, and the kind of material we're testing. So let's take a look at a few examples. This is a time versus flux for two materials. One of them is a nitramine-based propellant, and the other one an AP-based propellant, ammonium perchlorate being a very popular oxidizer, and nitramine being something like HMX or RDX. Okay, which one of these is the easiest to ignite? Which one? Well, the nitramine gasifies, but it doesn't reach go-no-go until it's way up here. It's the AP which gasifies and goes to complete ignition under these conditions, which is 100 psi. This one is the easiest of the two. However, you can generate a lot of reactive gas. Now, when we start to think about hazard, and we start to think about especially DDT, that's an important factor. Next, please. Okay, here we have an example of just AP, but now look, we've changed the pressure, 1 atmosphere. And we have our first light, first gasification. And here the difference in the two is fine versus coarse AP, the particle size. Okay, next. Keep that in mind. We're going to come back. That one's going to come back to bother you in a few minutes. A general observation, AP-based propellants will ignite and burn at low pressure with little or no pre-ignition time. Increased vulnerability to friction and fire stimuli, there's the hazard. And the relationship is there also in something called burn to violent reaction or fragment impact. The double base or nitramine-based propellants, which are often our 1,1 type materials, are more difficult to ignite at low pressure and often have a very long pre-ignition time. That contributes to the DDT problem. And within a family of propellants, this is why I said keep in mind that coarse versus fine. The higher the burning rate, the easier the propellant is to ignite. So now you're all going to be prediction. You're going to predict which one of those two AP-based propellants is going to have the highest burning rate. Fine, fine. Next. So let's talk about combustion. Very simplistic. Gas production in a closed or semi-closed environment is key to reaction violence. How much you confine it really is important. The opposite is, the sooner you vent, the more you can ameliorate your hazard. And it really can separate between propulsion, explosion, and even detonation. The burning rate is a characteristic of propellant chemistry. And however, something we use a lot is the mass burning rate is equal to the density times the burning rate, the characteristic burning rate, times the burn area. And I'm going to keep hammering on this. The burning rate is a function of pressure, and the burn area is a function of the physical condition, the geometry. Next. Okay, let's try our Delta rocket. This is a launch from
Florida. An unmanned Delta rocket carrying a $45 million military satellite is about to blast off.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We have ignition and liftoff from Cape Canaveral Air Station of the Air Force Delta II launch vehicle carrying a new GPS-2R satellite.
just seconds into the mission. An explosion rocks the cave.
We're just had an anomaly of the Delta II launch vehicle from Cape
That's an understatement.
We need to secure the area.
This is 1-3, folks.
250 tons of
1-3
flaming
propellant.
debris and rocket fuel rained down from the sky. The explosion occurred so close to the ground that the area around the launch pad looks like a war zone. A piece of the rocket lands in a parking lot, creating an enormous crater.
Remember what I said
More than
about
2
blast?
dozen cars are destroyed by the blast. The heat of the explosion is so intense it melts their windshields and tire rims. Amazingly, no one is injured. Investigators later determined that a 17-foot-long crack in one of the rocket's boosters was the cause of this devastating accident.
Crack. Surface area? Okay. This was in 2006. So not that long ago. We couldn't figure out how to embed it, so this is the best we're doing. And I think it worked out pretty good. You can find this on Google. So if you want to have it, that's where it came from. And I was told that some of the people at PRL worked on this, on Delta, after this incident occurred. So some people here at China Lake were involved in some of the studies that were done for this. Okay, so next slide. We take pictures too, but not quite so spectacular, and much, much smaller. This is a diagram of our high-speed. We use this to measure burning rates and combustion studies. We put a sample in a vessel, a windowed vessel. We use a high-speed motion picture camera to take a picture of it burning. Occasionally, we have to use illumination to look at the material itself. So I'm going to entertain you with a few more movies. Some people ask, what's the difference between minimum signature and what's smoky or fuel metallized samples? And the answer is there's no metal in minimum signature. If you have a sneaky airplane, you probably want to have a sneaky missile as well. So this is an example. Can you click on that? This is a very beautiful MinSig propellant. Very beautiful burning. You're looking at about 1/4 inch. This stand is a 1/4 inch wide. And the pressure of this one is 1,000 psi. Okay? Lovely picture. Now let's look at the metallized one. We can compare it to an AP-HTPB aluminized propellant at 1,000 psi. Not such a beautiful picture. Next. Okay, you're going to see that from a long ways away. Okay? That's the difference. Okay? Now, you notice how fast that goes. Let's look at the next one. Here we've slowed things down simply by going to a lower pressure. Next. Go ahead. So here's our metallized sample. Not quite a torch, but it's still burning quite nicely at 1 atmosphere. Now, okay, when we talked about a hazard, this propellant could become a hazard. And what's the flux these things put out? Now we need to understand what's going on. Perhaps we need to look at this material a little closer. So let's look at the next slide. Oh, okay, I'm ahead of myself, sorry. If we measure that movie, we can plot burning rate versus pressure. And here we are. Where's our fine in our coarse AP-based propellant that we saw the ignitability data for? And guess what? Finer makes a faster, higher burning rate propellant. There you can see it. Now, when we're interested in hazards, we're also interested in where does we get what is called the AP slope break. Slope, you can calculate the slope here in many areas, and that's used pretty often, something called AP to the nth. Burn rate equal to AP to the nth. And you can see now if you're over a large enough pressure regime, you can one of these. And when we change our slope, that's often referred to as a pressure slope break, or we want to understand, because up here where the slope is very high, a very, very small change in pressure makes a huge change in the burning rate. And that can be catastrophic. Also down here, if you're a handler at low pressure, like at atmospheric, you really don't want the thing to burn if you can help it. And that's some of the work that Amber and her team are working on right now, to make it so that these propellants, new propellants that are coming out, do not burn so well at low pressure. Okay, so now we'll go back. Go ahead, go forward. If we really want to understand what's going on the surface, we have to increase the magnification. And so that's what this is. Next. Now we're looking at that surface burning, and we can see the individual particles coming off, and we can start to understand just how aluminum is working and how it behaves. We can even track these things and look at the size of the particles. And my colleague that's here from France, I hope he can do some more of these for us, because we're really looking forward to having some more of these pictures. So next. So let's break it up. We talked about the crack. Now let's make a mess out of this thing. Next. To do friability, or to do what would sometimes called shotgun work, it's really two experiments. First, you have to damage the material, and then you've got to figure out a way to evaluate it. And so we use a high-impact device or a shotgun to damage the material, and then we use a closed bomb to evaluate that damage. And right now, to do that, this is a test that's actually used for hazards classification. It's called friability. We have to sleeve to follow the spec. We have to sleeve to 108 cubic centimeters. Next. Here's a layout of the experiment, very simple. We have a gun. We can fire it either with gas or a powder load, depending on our velocities. We fire it into a catch box. We gather up the debris, and then we test it further. Next. So here's the deal.
Do you propel the propellant sample?
You bet
or do
your
you
life.
Shoot the impact propellant?
We propel the sample.
Okay.
A cylindrical sample. That's why it's shown like a cylinder here. First, closed bomb theory, for those who do burning rates for gun propellants, you would fire a sample of known geometry, collect your pressure time history, use that equation that we talked about. The m dot equal to the density times the linear burning rate times the burn area, and you put that in the form of a geometric form function. You calculate your thermochemistry to get your m dot from your pressure time history, and you can solve for your burning rate as a function of pressure. It's done all the time. It's been done for years. Okay, let's get clever now. Let's say we damage that same material. We sub in our burning rate into this equation, and now we can solve for the area. Now there's an advantage to doing this. Now we can compare materials with different burning rates, because we've taken that out of the equation. Next. Okay, here is an AP HTPB-based propellant, undamaged, and at 2 different damage levels. We can fire these fast enough that we can turn them to dust. In fact, we can even ignite them if we go fast enough. Next. So if we plot maximum dPdt, or the pressurization rate, versus impact velocity, we can get some characteristic curves shown here. We have 3 samples. 2 of them are APHTPB-based propellants, and one of them is an explosive, PBX N109. It's HTPB-based as well, but RDX is the fill. RDX, all of them are aluminized. So this is part of the friability. You pass that test if you are less than 15 megapascals per millisecond at an impact velocity of 150 meters per second. Okay, 2 of them pass, right? These do. This one doesn't. Okay, but if we want to understand damage, we've got to go a little bit farther. We've got to take that burning rate out. Next. If we do that, then we look at our burn area versus impact velocity. Uh-oh, what happened? N109 is the one that has the most damage in it, as opposed to the two propellants. Okay, I'm telling you about the burning rate. I think that's the next slide. There's the comparison of burning rates. The two AB-based propellants have a much higher burning rate than our explosive, which actually burns quite atrociously. And we'll look at it here in a few minutes. Next. Okay, now we've really made a mess of things. We've got it into almost dust. Okay, next. One of the ways we study, and most recently, and that's what Anne, that's how I caught her attention, was I was talking about this experiment. And what we do is we throw a piston into a bed, a porous bed, a bed of energetic material. This experiment is the design of Harold Sandusky and Wayne Elbin. Sandusky is at NSWC Indian Head. I wish I'd invented it. It's a great experiment. The piston comes down, strikes the bed. Now we can instrument this bed to look at various aspects of what's going on in the powder. And we're using this right now to examine pyrotechnic powders. But it was designed for things like HMX. Next. So let's look at this. Okay, Kevin. Our piston is going to come down at 162 meters per second, strikes that bed. Now we see behavior, really two kinds of behavior coming along. We see that compaction wave, and then we see the great ball of fire, if you will. Next. We can take some frames, and I think you can see here very easily how we can make some plots of these two things. And these data have been used to develop a powder model which is then used to predict the behavior of this material in its design, in its system. Next. And here's the plot of the stuff you just saw. And there are the two various rates. Remember, it was 162. They go quite a bit faster. But they are a function of how fast we throw the piston. So this is, we've determined from flash X-ray studies as well, the compaction wave. And most recently, we've concluded that this behavior for this material is the friction on the walls. This material is highly friction sensitive. And so we're seeing the friction behavior on the wall, between the material and the wall.
You mean the friction heat generated by the friction?
Exactly, yes. Next. So, okay, let's take away the piston and look at thermal. So instead of using a piston, we will initiate this material thermally. Many times there's a difference in the sensitivity of a material whether it responds to a thermal or mechanical stimulus. Okay, next. Okay, this is for the explosive N5. And N5 is mostly HMX. It has 5%, I believe, of an inert binder, if you will. Or it's sometimes called desensitization material. So I would like to point out these numbers. We tracked that flame going through the bed, and we have 18 meters per second and 271. This is classic behavior for something going to DDT. Next. Here we have a plot of burning rate versus pressure. I've overlaid, here is the neat HMX burning rate curve. Let's just pick this number right here. This is 55 centimeters per second at 200 megapascals. I believe that's about 30,000 psi. And okay, we got a little discrepancy here. Remember the last one? Next slide. We have a rate, a big difference in the rate here. One of these wasn't really burning completely in the sense that we talked about complete combustion. And much of that is our pre-ignition time. It puts out light, puts out lots of light, and that was confirmed by our X-ray data. Most of it is the compaction wave that we're measuring. To let you know, Mr. Curran, who made these measurements, the flame was clear, or the apparent flame was clear to the bottom of the tube before any pressure was measured at the bottom of the tube. Next. This is the plate at the bottom of the tube. You can see where the bed stood there. There's a small indentation. This is at pore density. Okay, next. What if we take away that desensitizer and just do pure HMX? Next. The rates are almost the same, but there's the witness plate. So there's an example of the two. 5% makes a big difference in what you've added. Next. Okay, one of our more current work is the work on cook-off. And these are images taken from the Forrestal. The accident occurred in 1967. The Navy lost 134 people. This is part of the reason that I continue to work today, because this is a hazard that we haven't made a lot of progress on, even after all this time. Next. Thermal insult is of a particular severity for the Navy. When you're on a ship and there's a fire, you don't have a whole lot of places to go. The potential for fire is very high. The potential for ordnance to be involved is very high, and there is no getting out of it. Many fire scenarios are possible. You can come up with all kinds of things. We hear about different ones every day. For this regulatory issue, two are considered: direct exposure, which is often referred to as fast cook-off, and indirect exposure, which is called slow cook-off. In other words, the fire is adjacent to your store. Next. So, I am testing as you have to test with both of these. Slow cook-off, the conditions are 3.3 degrees C per hour. Comes under a lot of criticism. Everyone says it's unrealistic. There used to be the opportunity for a threat hazard assessment. Some of that's going away now with jointness. Whose threat do we use? You know, we use these ordnance items in many applications. Whose do we pick? So that's coming under scrutiny as well. Fast cook-off, the conditions are fairly widely accepted. This is where you put the item into a fuel fire. However, that fire is very difficult to control. It's pretty expensive to run that test. Environmental concerns are big. Germany right now has banned it. Okay, the use of liquid fire, like kerosene. Large diameter rocket motors become a particular problem because of their size, the amount of fuel that you need and the amount of time that's required to burn that fuel. So we need, from our perspective and from our opinion, we need an alternate test for that. Next. This is a small-scale test that we used in concert with some work we did jointly with the Department of Energy. And essentially, it's a pipe bomb. You cartridge load up your samples, heat the walls, and you measure what goes on. Next. Now, we're back to my drumbeat about surface area, porosity. This is LX10. It is another nitramine-based explosive. It's a pressed one. We're very fortunate. It's pressed at full density, 98% of theoretical maximum density. And this is the same amount of material pressed to only 75% of its maximum density. Now we're going to stuff it in that bomb and we're going to burn them, or we're going to cook them off, rather. Excuse me. Next. Which one was the most violent? Which one? This one. Okay. All we did was change the porosity. Okay. So I hope I've convinced you that surface area is important. Next. Okay, if I haven't convinced you, this is the explosive PBXN-109. We're going to look at two burning. One of these is the material as it was generated, as it was made, and the other one has been through a slow cook-off test. Turns out many times when we run slow cook-off, especially with this material, we can go out to the range and we can pick up pieces. Okay, so that's the one that's been through a slow cook-off. Okay, Kevin, let's look at them. Now, my combustion experts who are sitting back there will tell you that's really not very good. 30% char, even at 8,000 psi. Okay, let's look at the other one. Is it different? Okay. Now, if you're cleaning up a range, please be very careful about what you pick up after a cook-off event. Enough said. Next. So, fast cook-off. This is ongoing work. This is the work of Mr. Ford, who's sitting back there very kindly showing the view graphs. It was first started with respect to large diameter rocket motors and the difficulties in testing. It was supported almost entirely by the Department of Defense Explosive Safety Board, or the people that do hazard classification. But it's now very much of interest in insensitive munitions as well. And the key here is to have the conditions of a fire, but do it under a controlled environment. Control is the big deal. So here is a cartoon of the device, and since we're telling a story, this device was designed and built by our air breathing expert, Mr. Ken Wilson, over at PRL, just on the other side of this building, and it was nicknamed Alice's hairdryer. That's why you don't have any hair. The fan blows air. We inject liquid propane and burn it, and put the test article in the environment, a laminar type environment. And by changing the mass flow rate, the velocity, the amount of air you deliver, you can change the flux. Wonderful experiment, and it's great because we've incorporated some of our modeling and simulation all the way through this. They were key in helping us design this experiment. Jim?
Is the sample contained in anything, or is it just a bare sample?
It's contained.
Okay.
We'll get to that next. Here's a picture of it before it moved out to where it's now being used to be tested. Here's the fan, here's the injection area, the mixing chamber, and our witness plate. We can use one of these tubes as a witness plate. And this is a picture of the test article, Jim. So one of the important things is we have a flow diverter on the front end because we want all our flux to be delivered to our sample on the cylindrical part of the device and not create a hot spot in the front. And so even that was modeled so that we could have an optimum design. Next. I'm not going to say a whole lot about this because I want you to all invite Kevin to come and talk about this very soon. It was designed to replicate fuel fire fluxes, which run about 20 to 200 kilowatts per meter squared. Here's an example of how reproducible his experiment is. There are 3 of them here. 1, 2, 3. You might ask, what's this rise here? That's the tube starts to radiate, and we haven't got feedback built into the experiment yet. Here's an example of a fire. Same calibration tools, and you can see not too reproducible in the same fire even. Next. Jim asked about the sample or the test article, we like to call it. That's very, very critical. And so we instrument the material, we fill them. Kevin's gotten very clever. He can even put a bore in them. Amazing. And we insulate both ends because we're very much interested in what's going on in the center of that cylinder. Next. Okay, Jim, here's the difference between tactical steel, tactical composite, large diameter rocket motor. In fact, we simulated the rocket motor case of a large diameter and was 1/2 inch. Aluminum and composite. So this is just picking off out of those 13 thermocouples the change in reaction time. Okay, and Ephraim's and his team have been modeling this. Next. So I'm going to summarize because you're all bored and half of you are asleep. A variety of small-scale tests are used. We're using them all the time to gain combustion, understanding of both combustion and hazards. Ignition is the first step in the combustion process. Handling threats are a big problem if something's very easy to ignite. Long pre-ignition times are particularly of interest if we're studying DDT and that kind of behavior. Steady state combustion, it varies with pressure. No duh. And low pressure combustion is related to fallback and extinguishment. We saw a really spectacular fallback problem. High pressure burning rates are critical when we're starting to talk about DDT and XDT. I didn't mention XDT is unknown detonation transition. Changes in the burn area play an important role in the overall reaction violence. I hope I have, if I've left you with anything, I hope I've left you with that. And both it can occur both with mechanical, which we test with friability, and in cook-off. Next. I think that's, no. We have a subscale fast cook-off test. It has to mimic a fire. It is controlled, it is reproducible. I was recently in Meppen, Germany, because now we're trying to come up with an external fire, and this sounds like it's backwards, which will use propane. Small and subscale testing is really, really effective if you couple it with modeling and simulation. You need to have your modeling team really close at hand, either in your building or in a building that you can pick up the phone and get hold of them very quickly. It's used for design, for interpretation, and to predict. And that's where we're headed. We'd like to be able to predict. With these small scale experiments, we'd like to be able to predict what's going to go on in a full-scale environment. And it is, here's my mantra again, I'm on the box. Integration of small and subscale testing with modeling and simulation will result in a full-scale predictive capability, I hope in my time. Okay. I am dirt, remember. Okay. I think that's it, Kevin. Yes. Thank you.
Are there any questions for Alice this afternoon?
Go ahead.
When you're talking about surface area, are you just talking about how closely all the particles are packed together, or are there other geometries?
Oh, there are other geometries, yes. Yes.
How do you test those?
Well, the way we use it is with our closed bomb technique, and we just calculate an S over V, a surface to volume ratio. But there are, like some of the work Rick's working on, microscopic techniques to look at porosity in tersities. There's the SEM, which is a very, very good tool to, especially if you can apply some load to the sample, to look at binder-filler interactions. There are the tools like void content measurement and some of the mechanical properties. And those in concert with this really can give you a very good feel for what's the integrity of the material. I didn't mention it, but you can introduce about 5% void in high energy material and increase its shock sensitivity by an order of magnitude. I was talking about combustion today, not about detonation, so that's why I didn't bring that data.
Yeah, Alice, on that Delta rocket anomaly, you said that it was a 14-inch crack. Well, obviously you wouldn't put a rocket on a launch pad that you knew had a crack in it. How did they ascertain that at the end of the day?
You know, I don't know, Robin. To me, if it had that huge crack in it, I would think they would never have fired it. But some of the early work that we did with cracks, if you have a very small crack, that increases the time to get the flame from down the crack. In fact, as you become narrower, the velocity, the propagation velocity increases. And it's worse on the cracks you cannot pick up in X-ray. X-ray has a limit. But how they decided this was a crack problem, I'm afraid I don't have that data. I was looking for a spectacular picture, so.
So have you looked at aging propellants?
Aging?
Aging.
Yes, yes, we have. Particularly the effect of applied strain on burning rate and ignition. We were involved in a very extensive and very 5-year aging program, chemical aging. And on that particular system, it was not very great.
Okay, well, Alice, thank you very much. I have a certificate of appreciation for you,
thank
as
you.
well as a copy of your poster.
Okay.
So, Kevin, I know you're going to want this. Anne's going to get the calendar out, and you can sign up today for your program, okay?
Very good. Thank you very much.
We do have another program scheduled right now for July 16th. Maurice Ham is going to come and tell us about the aircraft that he helped engineer, reconfigure for the cloud seeding devices that they flew over Vietnam. So look for the information coming out towards the end of June, okay? Thank you.
Thanks.